Welcome to Lesson 2.1 on electrical potential. Last lesson, we were looking at Gauss's law continued. We did a couple of examples of working out electric fields, and then we looked at some uses of electric fields. This lecture, we're going to look at electrical potential energy. Then we'll go from that to electrical potential, and finally to potential difference, which is otherwise known as voltage. The first thing we'll do is look back at our comparison between electric fields and gravitational fields. You remember that Earth's gravitational field can be shown as arrows pointing inwards towards the center of the Earth. These gravitational field lines show the direction that anything with mass will fall if put near the Earth. Now, if you zoom in close to the surface of the Earth, the field lines start to look like parallel straight lines pointing downwards. And we can treat the field here as uniform, in other words, just having a constant value. Now let's look at gravitational potential energy. You might remember that it's defined as the work done bringing an object from infinity to a position a distance r away from a planet. Remember that potential energy always rises as you move away from a planet, and since infinity is the farthest you can get from anything, infinity has the highest potential energy possible. However, since the force is zero out there, that means no work is being done, so potential energy is zero at infinity. Since coming closer to a mass lowers your potential energy, all potential energies near objects are negative. And the closer you get to a heavy mass, the larger a negative value your potential energy will have, because it would take more work to pull you away. Notice that all you need to work out the change in potential energy is the starting and ending points. It doesn't matter what path was taken to get from one to the other. Now, when you look at the energy equation, you see that it is given here by U, which is potential energy, equals mgh. The mass is related to the particle itself, and the g and h are spatial quantities, because acceleration due to gravity depends on where you are in space, and h is the height it has risen in space. So if we just want to compare places in space, we need to get a quantity that is independent of the mass. So if we were to divide by the mass, we would get something we call the gravitational potential, that just depends on the strength of the field, that's g, and what is your height that you've risen in the field. Now let's look at something called equipotentials. Equipotentials are an easy idea. They are just lines or surfaces joining points of equal potential. So for gravitational fields, that means lines of equal height, and you can see them there above the flat surface of the Earth, and they're the horizontal lines. If you're cycling, going along an equipotential, in other words staying at the same height, doesn't really take much work if we're ignoring friction, but moving up in potential would take work. If you were going down in potential, work would be done on you, maybe too much, giving you too much speed, unless you apply the brakes. If you've ever looked at maps, the contour lines are equipotentials because they join points of equal altitude. Now you can see here that the equipotentials are at right angles to the field lines. This will always be true, even if it isn't a uniform field. You notice that all that matters is the change in potential. This shows part of a cycling course. You can see that you'd be doing a lot of work if you were headed uphill, in other words, rising in potential. But you'd be doing the same work if the whole track was lifted up by 200 metres or dropped by 200 metres. All that really matters is the difference in height between your starting point and your ending point. Electrical potential will be the same. We can work out the absolute potential at a point in space, but usually all we care about is the potential difference between 2 points. When we get away from the Earth, the equipotential surfaces are spherical, and you can see that they are still at right angles to the field lines. That satellite isn't changing its energy if it stays at constant altitude because there's no friction, so it can be moving at high speed with no work being done on it. However, if you had to lift it up to a higher altitude, you would have to give it energy. So the engines don't need to run just to keep it orbiting, but they would definitely have to be running to raise it to a higher altitude. Now let's look at the electrostatic case. We have a positive point charge in an otherwise empty universe, except for a little test charge Q0 at a distance r away from it. We know the electrostatic force between them. It's just F equals 1 over 4 pi E0 times Q0 over r squared. Now if r is infinity, then F is 0. So if we let the test charge go, it wouldn't move if it was already out at infinity, and that means it has 0 potential energy at infinity. But what is the electrical potential energy at the point r? It will be the work done by the Coulomb electrostatic force to push the particle back out to where the potential energy is 0, which is at infinity. To find the work done, we'll follow the working on a tablet. So I'll start with a positive charge here, Q, and I'm interested in knowing the potential energy at a point a distance away from Q. So the distance I'm interested in, I'll call it R. So we're heading out here, and that direction we'll call the R direction, but a certain distance along it, capital R, this is where I'm going to test the potential energy, and I will do that with a test charge plus Q0. And to work out what that potential energy is, I need to know the work done to move that charge from capital R, where it is, out to infinity, because infinity is the place where the potential energy is 0. The reason it's 0, remember, is that the potential energy is the work done, which is the force times the distance. By the time you're out here at infinity, the Coulomb force or electrostatic force is 0. So potential energy is 0 out there. So let's have a look at the work done by the field and moving out to infinity. And that will be the integral, because it isn't a constant force, so I can't just multiply it by the distance. I have to find the integral of force, and since we're going in the r direction, I'll make that the r vector. Usually when we have circular symmetry and radial lines, we will call it r rather than s. So this work will be, now we know the expression for the Coulomb force, it is Q0 over 4 pi E0 r squared dr, and bringing all the constant terms out the front, I now have just the integral r to infinity dr over r squared, and that will be Q0 over 4 pi E0. The integral of 1 over r squared, which is r to the minus 2, is minus r to the minus 1, and that is minus 1 over r, and again going from r to infinity. So the way I work that out, I put Q0 over 4 pi E0. Now I first evaluate that term at infinity, so 1 over infinity is 0, minus that term evaluated at capital R, which is minus 1 over r, equals Q0 over 4 pi E naught times 1 over r. So I'm just going to put the r down here. And that is my expression for the potential energy at r. So this is our expression for the potential energy. Now the potential, which is just a reference to the potential energy that's independent of the test charge, then will be the potential energy divided by the test charge. And so that will be simply Q over 4 pi E naught times R. So generalizing this to any distance along that axis, in other words, any distance r away from a point charge, we have the potential will be Q over 4 pi E naught R. So that means if we have our Q, then the potential will just depend on the distance r away. So we can see the lines where the potential would be equal are basically all these circular lines, or really if we're thinking 3D, they'd be spherical surfaces centered on Q, and all we need to know is the distance from that line from the point charge. But let's say we don't know what charges are there. Is it a point charge, several, a line of charge? Let's say that all we know is the electric field. Now we remember that the electric field is F over Q naught. In other words, it is the force per unit of charge. So another expression I could get for potential would be the work going from R to infinity over Q naught, or 1 over Q naught F dr going out to infinity, which would be F over Q naught dr. But of course we know that F over Q naught is E. So that gives us an expression for the potential at R being then the integral going from R to infinity, E times dr. But what we will often see it written as in textbooks, to keep it consistent, I suppose, with gravitational potential, they do it from infinity, so bringing the test charge from infinity to R, and then it is E ds. The sign really doesn't matter, because the thing to remember is that if you are coming close to a positive charge, you are rising in potential, because your potential energy for your positive test charge is increasing. In other words, it's got further to fall. There's another way of thinking of it, because that positive test charge, if you let go of it, would fall back away to infinity.